Hi everyone, I hope you all are doing fine. Since you already know that all the university courses have been moved online, the labs would be using LTSPICE from henceforth, and this is an introductory video to familiarize with the LTSPICE environment. The agenda here is discussing some introductory concepts of while using LTSPICE. To be able to run a simulation with right kinds of setups, and as a demo we will perform lab 6. Let's briefly discuss what the advantages and the disadvantages of a simulation tool is. Firstly, it saves a lot of time. It's very easy to edit on a computer. It's damn cheap. LTSPICE is for free for your information. And it's very safe, and of course we are now troubled with COVID-19 and very helpful in situations like that. The disadvantages being, well, you could have a simulation running, but it might still not run because there are some practical things which a simulation has not modeled, and that's one of the critical shortcomings of a simulation software is sometimes simulation results in an impractical design. So let's say you have some circuit to be made which in real life should go in a handheld device, let's say a mobile phone, and you design a circuit that would generate enormous amount of heat and would drain your batteries. Simulation software would tell you whether the circuit would work or not, but it's you who will have to decide whether it's feasible for a practical design. Well, the bottom line is simulation software is a very useful tool, but one needs to be very careful while running a simulation, because there's a big chance of entering a wrong component value or putting a wrong model of the circuit. So keep an eye out. So we'll begin with downloading the software. In this case, I won't be downloading the software. I'll share with you the download link. We will draw a schematic circuit from the scratch, put some component values, and run the simulation. Okay, so let's draw a schematic circuit. I will use the LTSPICE available on my computer. That's LTSPICE 17th. That's the button to start a new schematic circuit. So I'm going to demonstrate to how to attempt lab 6. So we need a diode which is 1N4148. I think that diode is available in the library. We'll find out that. This is the circuit that we need to make. So yes, go to edit, place component. You'll also notice that there are shortcut commands to invoke these specific routines. Now there are various ways we could model this part of the circuit. This is actually our function generator that we would have used in our actual lab. However, in a simulator you could choose to have a separate voltage source providing that offset, and a different voltage source providing a sinusoid, and a different resistor being treated as an internal resistance. Or you could also have just a simple function generator kind of thing which combinedly gives you the offset, the sinusoid, and the resistance. To place a component, go to edit, component, voltage, because that's going to be a voltage source. Can drop a component here. If you go inside the component and sorry, this is a right click inside a right click inside the component and press advanced. You will encounter many different programmings that you could do. Like it's actually like a function generator. So if you select sine, you can provide a DC offset, an amplitude, a sinusoidal amplitude, the frequency, and things like that. For this specific case, I would not merge all these three components into this model, but instead I will have a separate voltage source for a sine wave, a separate voltage source creating a DC offset, and an external resistor. So the DC offset for my source is going to be 0. The amplitude is 150 millivolts, and frequency is 5 kilohertz, so 5k. There is no delay, there is no phi, and these would be automatically pre-filled to be 0. So hit OK. That's sinusoidal source. I need one more voltage source to create an offset. A quick way to do that would be use Control C, copy this component, place it here. So that's inside the properties files of the second voltage source that we just copied. The functions is none. DC values has to be the offset voltage. Let me choose 0 for now, and that's done. Resistor control R. If you use control R, you could rotate the component. It's a quick shortcut button which I like, and hopefully you too. That's the second resistor. And now we need a diode. Go to edit, place diode, or you could go inside the component and find a diode from the library. Okay. To wire up the circuit, go back to edit, draw wire. Press the left button and connect the circuit together. Okay. One of the important things in SPICE software is the necessity to define a reference, and serves as a reference. Okay. The next step is to put values. Just ignore this. Your target offset voltage is 0.3. This diode is just a generic diode. We need to use 1N448. Right click on the diode, click on pick new diode, and here you go. The diode 1N4148 is available in the LTSPICE libraries. Yes. So yeah, the offset voltage is 0.3. So this is going to be 0.3, and we are actually ready to run the first step of the simulation to fill in the first row. Before you hit the run button, go to simulate, edit simulation command to fill in the simulation properties. The stop time is going to be 1 milliseconds, time step 1 microseconds. That should be fine for this simulation. Hit OK, place it here, and press run. Okay, the simulation is complete, and this is the input voltage. So this is 0.3, this is the mid level, and the amplitude is 150 millivolts. So it's 300 plus 150, which is 450, and 300 minus 150, which is 150. The voltage across the diode is this. So the output voltage is 430 millivolts here. So 430 minus 150 is 280. So 280 volts peak to peak. So DC offset is 0.3. Now, the DC component of the voltage across the diode is the middle point of the entire diode voltage waveform, which is between 430 millivolts to 150 millivolts. So the average is 430 plus 150 divided by 2. It's 290. So the DC voltage is also 0.2. We know that the AC voltage is exactly the same throughout all the test runs. So let me fill them up with 0.3. Okay, the next DC offset is gonna be 0.4. Press the run button. Okay. This is 480 minus 250, 480 minus 250, what's that, 250, 250, it's 230, so this is 0.23. The DC voltage (480 plus 250 to an average 365 millivolts. From that again. This is 520, as you can see across this corner of the screen. This is 520, and that point is 346. $175. Likewise, you could complete the entire table. So we're done with experiment 1. Moving on to experiment 2. Okay, by the way, how you can save the circuit and these waveforms that you got. Go to File, save uh, save plot settings if you want to save the plot. If you want to save the file, click on the draft because that's the circuit file. Save as lab 6, lab 6.1. Save. That's saved. You could also save the graphs the similar way. Go to save plot settings and they would be saved as .plt files. Or you could capture a screenshot if you wish. But let's close this thing and open a new schematics sheet for the second experiment. So we have a new file here. Let's start putting the components. To move a component, use that command. And we need one more resistor here. Okay. Let's join them together. To represent an oscilloscope, it's a good idea to put a resistor of a value of 1 megaohm, or you could skip that in this experiment. It should still work. Actually, better to write 1000K. This is 10 kiloohms. 10K. The value of the capacitance in this circuit is 1 microfarads. So let me put 1 microfarads here. The voltage source is a sine wave, 50 kilohertz with 0.33 volts peak to peak amplitude. So amplitude is going to be 0.15 volts or 150 millivolts. Frequency is 50 kilohertz. And there is no DC offset. What's the? And this is 50 ohms. For the first part of the experiment, we will consider the DC bias to be 0. That's when the circuit would be off, so we won't see any output here. Okay, the diode is 1N4148, and we are ready. Stop time 1 millisecond should be fine. Try to stop data maximum time step. In this case, I'm going to use 100 nanoseconds. Okay, the simulation is complete. So at a bias voltage of 0 volts, the output is, look at the output. This is in millivolts, 2 millivolts. It's barely nothing. It's just because the simulation software auto ranges the output. That's why we see some waveform here, but this is actually nothing. This is just 2 millivolts in comparison to the output, to the input, which is 150 millivolts in amplitude. The output is next to nothing. And the second part of the experiment would be to use a finite voltage here, let's say 2 volts, and see what happens. Oh, look at that. I'm sorry. Seemed to fit. This is the output voltage. Here we can see the value of the output voltage is now much higher than it was previously. It's 120 millivolts. So 120 millivolts is the amplitude, and the input amplitude was 150 millivolts. So this circuit is acting as a switcher. This is allowing the 150 millivolt amplitude to flow to the output when a sufficient voltage bias is connected across here. The next experiment is about the BJTs, the bipolar junction transistors, and we are going to see a relation between collector current and the base current for an NPN transistor. So here is our circuit. Okay, that's our circuit. So I have opened a new draft schematic. The transistors are available under the headings under PNP or NPN. Since we are going to deal with NPN transistor, I'm going to select NPN. That's the collector. This is our base. And we need a voltage source. So let's connect them up. That's the ground. There we go. Okay. Seems alright. Let's start putting the values in. So we are supposed to vary the base voltage from 1 to 25. So let's start with 1. Now, the transistor involved in our lab experiment is KSC 1008. We need to pick KSC 1008 if it's there. Let's see if we are lucky enough. Okay, seems that we are not as lucky as we were previously. To me, that looks good. I personally use this transistor. It's a very well-known transistor in the market. That's the model. So there are various numbers which define the characteristic of the device. We're not going to go into details of that. So let's simulate. So the simulation is completed. In our experiment, we are supposed to find the voltages across the resistors and then calculate the currents, and henceforth calculate the beta factor. However, since this is a simulation, we can directly find the current through the resistor instead of finding the voltage across the resistor and then inferring the current through it. So click on the component when you have that kind of symbol that shows the presence of a current. So this is the base current in 3.53 microampere range. This is the collector current. It is somewhere in 800 microamperes. So 800 microamperes and 3.53 microamperes. Gotcha. What's the beta factor? Let's find out. $226. Okay, so far so good. Now let's put 2 volts and simulate this again. Okay. The base current is around 13.2 microamperes. And the collector current is nearly 2.9 milliamperes. So the base current is nearly 13.2 microamperes. So let me put that here. And the collector current is nearly 2.9 milliamperes. The beta factor is 2900 divided by 290. $4.94. $23.23 microamperes. $314. Likewise, you could complete the entire table, and that's what you need for the report. With this, we come to an end of this demo. All you need to do is explore. There are many tutorials online as well. Here's my email.